Hello and welcome to learning decision trees with Python. Now, in this tutorial, we'll go through the intuition behind what a decision tree is, some of the salient aspects of the algorithm, as well as an example implementation with some data. Right? So, a decision tree is one of the most popular machine learning algorithms. It is one of the most interpretable algorithms because a decision tree is just a bunch of if-else statements. So let me give you an example, right? So let's go for a hypothesis like, does John play tennis? Now, given this question, I can have some data around it. So there can be a played variable, which can be thought of as a y variable, and it can either be a yes or a no on maybe 5 days that we captured data on. And this will mainly relate to some of the weather conditions, let's say. So let's capture how humid it is, or what's the temperature, and so on, right? So there can be a bunch of x variables, and we want to predict what the y variable is. Now, a decision tree finally, once it's built, will look something like, if temperature greater than, let's say, 20 degrees Celsius, then he has a particular probability to play, or something else happens, right? And then I can say here, if humidity greater than 80%, then he does not play, right? So this can be an n, and then, so if this is an n, then he does not play. And if it is greater than 80, then maybe he does play, right? So I hope you get the intuition behind what a decision tree will look like once it's built. It's a structure that has, through this example we can see, has a root node, branches, and leaf nodes. Now, each internal node denotes a test on an attribute. Each branch denotes the outcome of a test, right? So if I again go back, so this is the test of an attribute, and each branch is actually the outcome of that test. So the test is basically, is humidity greater than 80, or is temperature greater than 20? So if this is a yes or this is a no, things happen, right? So it's just a bunch of if-else statements flowing through graphically like this. Now, let's talk about what you can do with decision trees. You can solve regression tasks as well as classification tasks. And that's why classification and regression trees are acronymed CART. It's a very popular acronym that is used, right? So you can solve regression as well as classification with decision trees. Now I want you to go through some of the terminologies before we dive into the specifics of the algorithm and then the implementation. So we have the root node, which is nothing but the node with which the tree starts with. And then we have splitting. Splitting is the phenomenon of taking a question, and then based on whether the answer is yes or no, you branch out that particular node into multiple nodes, right? So that's the splitting part. Decision node, when a subnode splits into further subnodes, it's called a decision node. So if I have this node split into further subnodes, and then if I have this node split into further subnodes, all of these are decision nodes, right? Then you have the terminal node. So let's say if a decision tree ends here, then these at the peripheries of each decision tree, these will be your leaf or terminal nodes, because further splitting does not happen from here, right? So that's terminal node. Pruning, when we remove subnodes of a decision tree, the process is called pruning. It is the opposite of splitting. So if I come back here, I've built this decision tree, and let's say it's undergoing the classic phenomena of overfitting. So in that case, what we can do is we actually cut off some of these nodes, cut off some of these attachments, and then make the tree smaller. And what will happen is that you introduce some bias into the algorithm. It will probably take a hit on the training accuracy, but it will generalize well. on the test set, right? So this is called pruning the decision tree. We intentionally, deliberately cut short nodes in the decision trees so as to improve the generalization capability. There is a branch or the subtree concept. So a subsection of an entire tree is called the branch or subtree. So as far as this node is concerned, this is a subtree, and then this is also a subtree. And then as far as this node is concerned, this is a subtree, and then this is another subtree. So you see where this is going, right? Every time a node splits, everything to the left of it and everything to the right of it are two separate subtrees respectively. And then there's, of course, a parent and a child node concept. A node which is divided into subnodes is called the parent node, whereas subnodes are the children of a parent node. Easy enough to understand. So just to drive that point home, this can be thought of as a child, and in that case, this will become the parent. Okay? So that's how this will work. Now let's come to the intuition. Again, it's one of the most frequently used supervised machine learning algorithms. You can do both regression and classification tasks. And the intuition is as follows. For each attribute in the dataset, the decision tree forms a node. The most important attribute is placed at the root node. Okay? For evaluating the task in hand, we start at the root node and we work our way down the tree by following the corresponding node that meets our condition or decision. The process continues until a leaf node is reached. It contains the prediction of the outcome of the decision tree. So again, all of these notebooks and artifacts will be available to you. So I'm not worried about reading things off of a Colab notebook, but let's just go through an example to understand what exactly is going on. So I'll just erase everything that I have so far so that we can start with a blank slate. So let's come back to our tennis example. So let's say we have temperature, and then we have humidity, and then to keep it simple, let's just say those are the two factors, and then we are supposed to predict whether John plays or does not play tennis on that given day. Now, given this, we are expected to build a decision tree that will eventually lead to an outcome or a decision whether John plays tennis or not. But if I want to start building the decision tree, I need some strategy of how to select the root node. So the root node can either be, let's say, temperature greater than 20, or it can be humidity less than 80. Which one do I pick? Why these arbitrary values then? Why does temperature have to be greater than 20 or humidity has to be greater than 80? Why pick temperature at all when I can pick humidity and vice versa, right? So these are some of the dilemmas we can face while building the decision tree. There is a mathematical clear-cut representation on how to pick the best node, right? So let's say we have some magic formula at our hands for now. We'll definitely go through it. That how to pick the best node. Now, if I have the strategy ready, then let's say this comes out to be the one and this becomes my root node. So if it's a yes, things can happen, and then if it's a no, we can continue the algorithm, right? So let's say we discover that if temperature is greater than 20 and humidity is less than 80, then John always ends up playing. He does not play during these times, and he does not play during these times. And voila, we just repeated the course of the algorithm by asking questions, mathematically selecting the best node, which we'll come to later, and then eventually landing on leaf nodes that contain the decisions. So if there is a new data point that I'm supposed to predict in the future whether John might play tennis or not, I just have to plug in the values of temperature and humidity, run through these questions, run through these if-else statements, run through this decision tree, and I will be done. Whether or not that data point lands on this one or this one or this one will drive what my prediction is going to be. So let's come to attribute selection measures. So which attribute do I select as my root node, and then after that is done, what will drive the decisioning behind subsequent node selections or attribute selection measures? The primary challenge in the decision tree implementation is to identify the attributes, like I just told you. So what we can do is select one out of two very popular attribute selection measures. Number one, information gain, and then number two, Gini index. Now, while using information gain as a criterion, we assume attributes to be categorical, and for Gini index, attributes are assumed to be continuous. These attribute selection measures are described below. So for example, temperature can be thought of as a continuous variable because it can lie anywhere in the spectrum on the real number line. Whereas, let's say, location, if you're trying to use location as a variable that has four values, east, west, north, south, then what you would do is tend to use the information gain, right? So that's the general rule of thumb. We assume attributes to be categorical for information gain and continuous for Gini index. Okay, so let's go through information gain. The number one thing you need to understand about information gain, or if you want to understand how information gain works, you'll have to understand what is entropy. Now, we've got this kind of complicated looking equation here, but what we can do is simplify this drastically, right? So it has a summation from 1 to c, c being the number of classes, and then minus of pi times log pi base 2. Okay, so this is a very interesting metric that will be clear once we expand on this, right? So entropy, it says, is basically minus P1, or rather let's say P0 log of P0 base 2 minus P1 log of P1 base 2. So what I did here was just expand upon that summation equation. Let me just get rid of the other stuff so that we can have nice clean slate to work with. There we go. So entropy, if I just expand that equation, it was a summation of 1 to c, c being the number of classes. So in this example, we have two classes, P0 and P1. So P0 is basically the probability of the occurrence of class 0, and then P1 is the probability of occurrence of class 1, and then we have the logarithms. Now let's just analyze what is happening here. So let's say the probability of P1 is 0.5 is something that comes out of the prediction, right? So what will P0 be? Of course, it will also be 0.5 because they have to sum up to 1. Now, if I plug in these values here, what will happen is minus 0.5 log of 0.5 base 2, and then minus 0.5 log of 0.5 base 2. Now notice here, I can just write 0.5 as 2 to the power minus 1 because 2 to the power minus 1 is half, and you get the point, right? So I can plug that in here, and then this becomes minus 0.5 log of 2 to the power minus 1 base 2 minus 0.5 log of 2 to the power minus 1 base 2. If I simplify this further, the minus 1 can come in front, and then log 2 base 2 will simply be 1, right? So if I bring the minus 1 in front, it becomes 0.5. The negative sign is cancelled off, and then if I bring the minus 1 in front here, then it will become a plus of simply 0.5 because log base log 2 base 2 will be 1. And then it eventually leads to 1. So whenever P0 or P1 is 0.5, the entropy seems to be 1. Now let's just go through another example where P1 is 1, which means P0 will be 0. Now what will happen to entropy in that case? So P0 vanishes, so the entire term here vanishes, and we are just left with minus 1 log 1 base 2. Okay. Now, interestingly, since this is log 1, or log 1s are 0, because I can write this 1 as minus 1 log of 2 to the power 0 base 2. The 0 comes in front, and this whole term vanishes as well. So we not only manage to vanish this expression, but also this one, right? So eventually this leads to 0. So whenever P1 is 1, or for that matter P0 can also be 1, it will lead to the same outcome. The entropy is 0. So this is very interesting, and this is where the intuition comes in. If I'm completely confused about what the prediction has to be, and this is evidence of confusion, right? You're literally saying I'm 50% sure it can be class 1 and I'm 50% sure it can be class 2. In that case, the entropy is highest. It's put in as 1. But if you're absolutely sure on the opposite direction, 100% confident that a particular prediction has 100% probability of being the first class, then I drive entropy down to 0. So entropy is a metric which seems to be paying a lot of premium, or rather seems to just go down to 0 if you're absolutely sure, and shoots up if you're absolutely unsure. And then anything in the middle will emanate values between 0 and 1. The higher the entropy, the less confidence the model has. So that's why if a model is not confident enough, it has to pay a higher price, right? So greater the entropy, worse it is. Just remember this. Okay. So I hope you have the intuition of what entropy is. And then Gini index, I'll just leave that as an exercise. It works along the similar lines. And information gain eventually is a measure that is based on entropy. So it is the difference in entropy between the parent node and the child node. So let's just complete that thought. So let's say I have a decision tree that looks like this, for example. So here I will have entropy 1, and then I will have entropy 2, I will have entropy 3, entropy 4, and entropy 5. So at different nodes, I will have data points and different values of entropy, right? So let's say I started with 100 data points. 70 data points came here because there was a decision being made, right? Let's say temperature is greater than 20, whatever. So 70% of the data points came here, and then 30% came here, let's say. So the information gain of this particular split will be E1 minus 70 times E2 minus 30 times E3. Okay. So if I measure the difference between the entropy, what I will get is called information gain. Okay. So information gain is simply the difference in the entropy of a parent node and its corresponding child node. And this is exactly how I will choose what attribute to split on. So for example, if I have a dilemma here, of splitting between temperature and humidity. What I will do on that case is measure the difference in entropy or the information gain for the temperature, and then I'll do the same thing for humidity, and whichever gives me the highest information gain. So the difference in entropy, the larger it is, the better. So information gain, the larger it is, the better. And whatever attribute gives me the largest information gain will be the attribute I will select to split my decision tree, right? So Gini index, again, I'll just leave that as an exercise because it's something that is very similar. Now let's come to overfitting. Now overfitting, again, we all know about it, so I won't waste your time explaining what overfitting is. It's there in the beginner machine learning courses that we have done already. The two approaches to rectifying overfitting in decision trees is pre-pruning and post-pruning. Now, what is pre-pruning? We stop the tree construction a bit early, again, deliberately, consciously. In pre-pruning, we prefer not to split a node if its goodness measure is below a threshold value. But again, it is difficult to choose an appropriate stopping point. So if I say I keep working on this data set and my decision tree is getting abnormally large, and I can sense that there is a scope that this will overfit, right? If it gets abnormally large and deep, for example, then what I will do is set a threshold on the information gain. So if the information gain is not above a certain threshold that I can set based on the use case, based on the data, different industries have different benchmarks on this. Based on that, if I want to set a threshold, what will happen is, if the information gain is not beyond that threshold, the split won't even happen. It stops. And that's pre-pruning for you. We deliberately introduce bias into the algorithm so that it can generalize well on the test data. Now in post-pruning, however, we let the tree build by itself fully with no restrictions first. So we let the tree go deeper and deeper, however deeper the algorithm wants me to go. And then once it shows the overfitting problem, then pruning is done as a post-pruning step. So we use the cross-validation data to check the effect of our pruning. So what I mean by that is, we let this tree grow in the training step. We don't stop or we don't put thresholds of any kind here. And then once the tree is built, I can get evidence of overfitting through cross-validation, of course. And then let's say I snip off this part and then reevaluate the decision tree on the cross-validation set or the test set, or typically the cross-validation set, because you don't want to do that to this. You don't want to fine-tune your algorithm on the test set, right? So on the cross-validation set, snip off a couple of leaf nodes or a couple of nodes and then reevaluate the algorithm. And if the drop in accuracy is not very significant on the cross-validation set, then we continue pruning, or we can say this is enough pruning, we stop. So depending upon the loss in accuracy on the cross-validation data set, we can go around the large decision tree that we have built and then keep pruning parts of it just to sleek it down, and again deliberately introduce bias. Okay, so with that, I think you're kind of ready to understand how decision trees work and to go through an implementation of the same. So I'm going to import the required libraries here. And then I'm going to import my data set. Now, again, EDA has to be way more comprehensive than what I'm showing, but the focus of this lesson is to learn decision trees, right? So whatever we have covered in the EDA section still holds true. It's just that I'm going to be lazy and skip a bunch of steps so that we can get to the decision tree quickly. So I have 1728 data points with 7 columns. Let us quickly look at the head. A couple of things don't look right. There should be column names. and that's there in the metadata of the data set. So I just plug that in and then assign df.columns to the list of column names and then preview it again. And then now I have column names here and they now have meaningful names. So if I get a quick info on this, then all of them are not null and all of them are objects. So let's quickly go through the frequency distribution of each. So what I'm doing here is taking each column and then getting the value counts. So this is basically, think of it in the SQL world like group by that particular column and then get the count star of that, right? So seems like for the buying variable, very high, high, medium, low are all evenly distributed, and fairly so is the case for the other attributes as well, apart from the last variable, which is class, which seems to be a little skewed towards this particular value, right? So now we can see that the doors and persons are categorical in nature, so I will treat them as categorical variables. The rest of them will be continuous. So if I look at the summary of the variable, class is the target variable. There are 7 variables in the data set, and if I look at class, this is where the slight imbalance resides. Now think of what variables are. They can be discrete or continuous, and then discrete can also be ordinal or nominal, right? Now this seems to be ordinal in nature because very good is better than good, is better than this, is better than this, right? So what we can do is encode it as an ordinal variable. So if we set a value of 5 to this, maybe we can set this to 4 and set this to 3 and set this to 2 and so on, right? So one can be greater than other will make sense for this data. We do not need to use one-hot encoding or other such forms of categorical variable encoding where the values are independent of each other. Again, going back to an example like location, east, west, north, south, you cannot encode them numerically like 1, 2, 3, 4 because east is not greater than west. That just does not make sense, right? So if I check for missing values, there are no missing values, which is good news. So saves us a bunch of trouble EDA wise. For my x, I'm just going to drop my y variable and then just include my y variable as part of y. And then I go for the train test split. You should all be familiar with this by now, given that you've taken the beginner's course. So if I look at the shape, I've split it into 33% test data and the rest of the 67% as my training data. Okay. Now quickly we'll go through some feature engineering. If I look at the data types, all of them are objects. We'll encode the categorical ones like we had seen before. We'll install this or upgrade this quick library. Import category encoders, and then I'll encode these variables as ordinal encodings. And again, the reason why we are doing that is the values here are ordinal. Very high is better than high, high is better than medium, medium is better than low, right? So I can easily encode them as ordinal encodings, but in other cases where these categorical values are independent of each other, you need to go for the one-hot encoding. So that's how my training set looks like. And again, you can see that it is a nice random split where the index are all jumbled up. And then we finally get to building a decision tree. So using the decision tree classifier, Criterion, I've set to Gini index, max depth is 3, random state is 0. So what I'm doing here is again something we went through called pre-pruning. So I'm saying the maximum depth that you can attain in the decision tree is 3. Beyond that, no splitting, right? So again, this is a means to control overfitting. So if I have a decision tree that goes like this is level 1, this is level 2, and then this is level 3, there'll be no further splitting after this, right? And again, this makes some sense because we only have 7 variables to deal with. Going beyond a depth of 3 will definitely lead to overfitting, right? And then random state, this is again something that we set so that the results are replicable, so that if it is going through any form of random number generations inside the algorithm, those can be replicable. So once the class is initialized, I will invoke a dot fit on this and then do a predict on the test set and then check the accuracy scores. So the model accuracy score with Criterion Genie is almost 80%. Nice. Let's compare the train and test accuracies because we want to check for overfitting, evidence of overfitting. The training accuracy is 78%, the test accuracy is 80%. You can see that they're kind of similar. They aren't deviated a lot from each other. So if I bring them both together, the training set is 78% and the test set is 80%. I think we are good with this, right? And if I want to visualize the decision tree, that what I've made here with the different values is that x of 5. So this is the 6th column in my data. So if I look at the 6th column in my data, that is safety. So it says safety less than 1.5. Now I have encoded them ordinally, so it will never actually assume the value of 1.5, but that is how averaging works, right? So if it is less than 1.5, that is typically it will be either a 1 or depending upon how this has been encoded, maybe a 0, I'm not sure. If it is greater than 1.5, then it goes over here. And then again, x of 3, which is the 4th column in my data, the person's column. The person's column is checked here, and if it is less than or equal to 2.5, if it is a yes, it comes here. If it is a no, it comes there, right? You see where this is going, and we can use another library to kind of color it up, touch it up a little cosmetically, and this is how the decision tree will look like. Now imagine just sharing this with a business stakeholder who has no knowledge of data science, no technical knowledge, how interpretable this will become, right? I can remove things like Gini, the concepts that they might not understand, but this is very interpretable, right? So if persons is less than equal to 2.5, then the class is this. And then if you want me to go further, if this particular criterion is false, then I go here and the class is this. Or I can go further and the decisions will reside in my leaf nodes, right? So we can traverse down this tree. One of 3 things will happen. Either I land here or here or here, right? So accordingly, the classes are determined. And then again, this is another leaf node, by the way. So the decision tree classifier with entropy, I can see that all of these values are coming to one particular value only, and that will probably be the skewed value we looked at from the start. So this is where we kind of get into imbalanced data classification problem, probably a problem for a later lesson, right? So this time let me use entropy instead of Gini. The rest of the parameters remain the same, and see if I'm getting some sort of a lift. So model score is again 80%. I don't think this has been significantly helpful compared to using Gini. So again, we are pretty much the same with respect to train and test accuracy, 78 and 80%. Check for both, they're fine. And then finally, visualize them. And instead of giving cryptic names like f of 5, I can have a nice graph viz and then have the actual column names show up here, right? So that is a quick lesson on decision trees. So what we went through here, and I can also run the confusion matrix and the final classification report. So this has the precision recall, the F1 score, and the supporting number of data points here. And then you can easily see that there are 25 data points that are very good, and we didn't do anything about it because nothing was predicted, right? Nothing was predicted is good as well. So this particular algorithm or this particular implementation might need further pre-pruning or post-pruning depending upon how you want to conclude it. But the objective of this lesson was kind of to go through what a decision tree is, how it works, and how it is implemented in Python, right? So the different criterias we can use, the different parameters we can play with, and of course, if you're further interested, I've kept in a bunch of references so that you can do a further study of this. I really hope you enjoyed this lesson on decision trees. Thank you very much.